So we've seen that the effect of the atmosphere on surface temperature is to generally warm it, more in some cases and less in others. What's the main cause of this warming? Well, that's called the greenhouse effect. Here's how it works. Solar radiation powers the climate system. Now, some solar radiation is absorbed by the atmosphere, some is reflected by the Earth's surface and by the atmosphere, but about half the solar radiation is absorbed by the Earth's surface and warms it up. Then, as we said, things that get warm emit thermal radiation, so this thermal radiation is emitted from the Earth's surface in all directions. And what happens is that some of this thermal radiation passes through the atmosphere, but a lot is reabsorbed, and what's reabsorbed is re-emitted in all directions. Now that happens due to clouds and also due to greenhouse gas molecules. So the basic effect is to warm the Earth's surface and the lower atmosphere more than it would have warmed if the atmosphere weren't there. So why do Earth, Mars and Titan have different amounts of the greenhouse effect? Well, because they have different amounts of atmosphere and also different atmospheric compositions. This just shows the major atmospheric gases on Earth, Mars and Titan. Now, Earth's atmosphere is about 4/5 nitrogen and 1/5 oxygen. Mars's atmosphere is mostly carbon dioxide with a little bit of nitrogen. And Titan's atmosphere, like Earth's, is mostly nitrogen, but it has just slightly more methane than Mars has nitrogen. So what is a greenhouse gas? What do we mean by that? Well, what we mean is that it's one that lets through most of the solar radiation, but which absorbs and then re-emits some of it back to the surface, a lot of the thermal radiation that's emitted from the surface. Carbon dioxide, or CO2, is a major greenhouse gas. Only a very small amount of CO2 causes a very large amount of extra warming. Other major greenhouse gases on Earth are water vapor and methane. And now, although water vapor is produced naturally, the problem is that a warmer atmosphere can hold more water vapor. So this results in a positive feedback because as the atmosphere warms up, it can hold more water vapor, and more water vapor causes the atmosphere to warm further, and then the atmosphere can hold even more water vapor, and so on. So why isn't Mars warmer? On Earth, too much CO2 is warming up our lower atmosphere and surface too much, even though it makes up less than 0.1% of our atmosphere. But Mars's atmosphere is mostly carbon dioxide. So why does Mars have such a small greenhouse effect compared to Earth, only 5 Kelvin? Well, it's because Mars has so little atmosphere and such low atmospheric pressures. Just have to talk about what surface pressure is. It's basically just the force of air pressing down on the surface at any point. So it's given by the amount of air above you when you're standing at the surface multiplied by the gravity of the planet that you're standing on. So that means that turning this around, the amount of atmosphere of a planet per unit surface area is given by the surface pressure divided by gravity. So we know the surface pressures on Earth, Mars and Titan. On Earth, gravity is 1g and the surface pressure is 1 bar. On Mars, gravity is just under half that on Earth, but the surface pressure is hugely smaller. So this means overall that Mars has about 70 times less atmosphere than Earth per unit surface area. On Titan, gravity is even smaller, and the surface pressure, though, is 50% larger than on Earth. So in fact, this together means that Titan has about 11 times more atmosphere than Earth per unit surface area. So why is Mars's greenhouse effect so much weaker than Earth's? Well, it's because it has 70 times less atmosphere to capture solar or thermal radiation. Now, it still does have, if you work it all out, about 30 times the CO2 we have on Earth, but that CO2 is at much lower pressures. And the way the absorption of radiation works, CO2 actually absorbs a lot less at lower pressures than it does at Earth-like pressures. And in addition, Mars also has far less water vapor than on Earth, 0.03% compared to a few percent, and that works out to about 5,000 times less water vapor. And Mars doesn't have significant amounts of any other greenhouse gases. So overall, Mars has a very weak greenhouse effect compared to Earth. Oh, just one last thing about surface pressure on Mars. Mars has a similar tilt and hence seasons to the Earth, and we'll talk more about this next time. And you can see that during a southern summer, the southern hemisphere is tilted towards the sun, and in northern summer, the northern hemisphere is tilted towards the sun, just as on Earth. And what that means is that the winter poles actually get cold enough on cold old Mars for the carbon dioxide that makes up most of Mother's atmosphere to freeze out onto them. And this just shows the amount of CO2 that's at the north and south pole as frozen CO2 ice at different times of year. So what this means is that the total mass of Mars's atmosphere changes over a Mars year depending on how much of it is frozen out at any given time. And because surface pressure is just the mass of atmosphere above us, this means that the surface pressure changes through a Mars year. And this just shows the Viking lander measurements of surface pressure as a function of time of year. Now, every rover or lander sent to Mars has measured these same changes in the surface pressure over a Mars year. So let's finish by looking at temperatures in the atmospheres of Earth, Mars, and Titan. We define layers of the Earth's atmosphere according to how the temperature behaves in each of them. And it depends on how temperature varies with height. So the lowest layer is called the troposphere. Most clouds appear in the troposphere because 99% of the water is found here. Temperatures decrease with height in the troposphere because the air is heated by the surface and cools as it rises. The next layer up is the stratosphere. This includes the ozone layer, which absorbs the sun's high energy ultraviolet or UV rays. This is what causes temperature to increase with height in the stratosphere, as you can see in the figure. And the ozone layer also prevents harmful UV from reaching us at the surface. Above this is the mesosphere, which means middle atmosphere. Here, temperatures decrease with height again because there's little local heating. Now, the coldest temperatures in the Earth's atmosphere occur at the mesopause, which is at the top of the mesosphere. And finally, the top layer is the thermosphere. It can extend up to 1,000 kilometers sometimes, so only a tiny part of it is shown in this figure. Here is where most of the highest energy solar radiation, for example, X-rays and extreme UV, is absorbed before it reaches the lower atmosphere and surface. So as a result, temperature increases with height again in the thermosphere. And the exosphere that we talked about right at the beginning is above the top of the thermosphere. Now, auroras occur in the thermosphere, and the International Space Station also orbits in the thermosphere and in the exosphere. What about the atmosphere of Mars? Well, as on Earth, Mars's troposphere is warmed by surface heating from below, so temperature decreases with height. And also, as on Earth, in Mars's thermosphere, the temperature increases with height due to the sun's highest energy radiation being absorbed there. But that's all for when Mars looks like this. What about when there's a global dust storm? Well, Mars's atmosphere changes when big dust storms occur. Now, normally, as we said, Mars has a very thin atmosphere, and you can see these clouds hanging out there in the atmosphere, and it looks pretty easy, pretty good visibility maybe. And it only forms thin clouds of water or carbon dioxide ice. So we're not getting a lot of clouds getting into the atmosphere and changing the way that radiation is absorbed or scattered, very much anyway. However, when you get a lot of dust lifted off the surface and into the atmosphere, it produces big dust storms. And these happen for reasons we aren't quite sure about yet. And that's one of the things I spend a lot of my time working on. And we'll talk more about how this happens and what it looks like in a later program. So global dust storms can hide the surface of Mars for many weeks on end. And they also have a huge effect on Martian temperatures. So what they do is they warm the atmosphere. So most of the time, as we've talked about, Mars's thin atmosphere absorbs very little of the incoming solar radiation. So it's mostly heated from the surface below. But during a big dust storm, there can be 50 times more dust in the atmosphere. And dust absorbs solar radiation and warms the atmosphere where the dust is. So atmospheric temperatures, certainly in the middle atmosphere, can go up by over 90 degrees Fahrenheit, that's 50 Kelvin. Another effect of Mars's thin atmosphere is the time of day variation of temperature. So because thermal radiation escapes so easily, Mars's atmosphere and surface cool very rapidly at night. So temperatures near the surface of Mars easily fall over 125 degrees Fahrenheit or 70 Kelvin below their peak afternoon values, and that happens all over Mars. Isn't it all rare? By contrast, in Altadena, the daily temperature range is more like 30 degrees Fahrenheit. That's only a measly 17 Kelvin. Now, the all-time record for Earth is over 100 degrees Fahrenheit, but that is extremely rare and always due to very weird weather. So basically, Mars is a very much more extreme planet in terms of its surface pressure and temperature variations than Earth. What about the atmosphere of Titan? Well, the high atmospheric pressure means that Titan's atmospheric gases absorb and re-emit thermal radiation very effectively. So it has a pretty strong greenhouse effect. However, it also has a thick haze layer above that, above the lower atmosphere. And that haze actually absorbs or scatters 90% of the incoming solar radiation, and it really warms up the upper atmosphere. But that haze doesn't absorb or re-emit any outgoing thermal radiation. It lets that all go right through. So basically, it blocks solar radiation getting in, and it lets thermal radiation escape, and that works against the greenhouse effect. So that means that the surface is colder than it would be without the haze, although it's still warmer than it would be without any atmosphere at all. So Titan's thick haze actually makes it impossible to see the surface in reflected sunlight, which is how we see things with our human eyes. And that's because the atmospheric haze particles absorb or scatter most visible light before it can even get to the surface. But some infrared wavelengths of light are much less affected by the haze. So if we look at Titan in those infrared wavelengths, we can see surface features.